ib1 students in our next video lesson. Today I'm going to finish this topic related with ideal gas, and I'm going to finish a chapter, thermal physics. Yes? Let's start with your homework. Thank you, most of you sent me homework, and most of you did the homework correctly, but not all to you. So let's check one by one. I'm not talking about final answers because unfortunately my calculator doesn't work, it's broken, I must buy, but where? Okay, so I'm going to focus on the method, not on the final answers. Then we will do together two exercises, one easier like warm up, and second a kind of difficult, so specific. I'm going to present you the most general method, maybe not the best one, because there are shorter methods to solve this problem. And finally, I have to focus on Boltzmann equation, something which links temperature, absolute temperature in Kelvin scale, with kinetic energy of gas molecules. And then maybe we'll do a exam paper. Okay, so let's start with exercise number 18 in your Tsokos. I'm going to copy exercise number 18 to the screen here. Okay, a gas has a pressure 8.2 times 10 to the power of 6 pascals, volume 2.3 times 10 to the power of minus 3 meters cubed. The pressure is reduced to one which is given. At constant temperature, calculate the new volume of the gas. So let's look. The base is Clapeyron's equation, PV equals nRT. But if amount of gas is constant, you can write this in the form that PV over T is constant. So in this case, you have information that temperature is constant. So when temperature is constant, then it can be written as P times V is constant, so pressure times volume at one state must be equal to pressure times volume at other state. And we know pressure 8.2 times 10 to the power of 6 standard units, volume 2.3 times 10 to the power of minus 3 standard units must be equal to new pressure 4.5 times 10 to the power of 6 standard units, and new volume, let's name this V2. So you can cross 10 to the power of 6, and you have finally this times this, so 8.2 times 10 to the power times 2 to the dot 3 times 10 to the power of 3 minus 3 divided by 4.5 in meters cubed. Okay, not difficult, easy, in my opinion, easy. Okay, exercise number 19. Let me copy here and solve this. I hope you are checking and your answers are the same or almost the same. Okay, we have 12 kilograms of helium. A mass of 12 kilograms of helium is required to fill a bottle of volume 5 times 10 to the power of minus 3 meters cubed at a temperature of 20 degrees Celsius. Determine the pressure of helium. First of all, standard units. The temperature 20 degrees Celsius must be converted into Kelvin, so it's 293 kelvins. We have a volume which is 5 times 10 to the power of minus 3 in 3 significant digits of meters cubed, so this is a standard unit. But we have a mass. You have to find number of moles because again we have to use Clapeyron's equation. So helium has a molar mass of 4, we did this, which means that 4 grams of helium is 1 mole. Okay, so 12 kilograms is 12,000 of grams, so you can use simple proportion to find how many moles is needed. Okay, so this times this equals this times this, so number of moles is equal to 3,000. Okay, so we know that number of moles of this helium is 3,000 of moles. Remember, in this writing, this is mass in grams, which corresponds with 1 mole amount of substance. Okay, and finally, again, Clapeyron's equation, PV equals nRT, and the question is about P, so P is equal nRT over V, N is 3000, R is a gas constant given in your data booklet, 8.99, probably 8.99, let me check, it's here, constant R, 8.31, sorry. Okay, times temperature, 293 kelvins, divided by volume, which is also given 5 times 10 to the power of minus 3. So finally you can calculate pressure here, a little bit more advanced than previous, but still not too difficult. Okay, so still we have to do exercise number 21 and 22. So next slide, exercise number 21 first, and 22 you had to try. Okay, exercise number 21. We have a flask of given volume, okay, which contains air at given pressure. Yeah, so we have volume, we have pressure, and the temperature, remember, temperature must be converted into Kelvin, so 27 degrees Celsius is 300 kelvins. Okay? We have volume of 300 times 10 to the power of minus 6 in 4 significant figures, and pressure, which is 5 times 10 to the power of 5 in 3 significant digits. And we know that flask loses molecules at rate of, so the number of molecules which is lost in unit time is 3 times 10 to the power of 19 molecules per second. Again, in 3 significant digits. So molecules, not moles, molecules per 1 second. Estimate how long it takes for the pressure in the flask to fall to half its original value. Assume that the temperature of the air remains constant during the process. So again, PV equals nRT. Okay, we know that the volume is constant because this is a flask. R is constant, and it's written that temperature of the air remains constant, so T is constant. What does it mean? It means that pressure in this case is proportional to number of moles, and remember that number of moles is proportional to number of molecules. Yes, because number of moles multiplied by number of molecules is Avogadro. Number of moles multiplied by Avogadro constant is number of molecules. Okay. So basically, if you want to find a time after which pressure drops to half, yes, then you have to first find how many molecules is in the flask at the beginning. Okay, so use Clapeyron's equation and calculate a number of molecules. So first calculate number of moles, which is PV over RT. P is given, is 5 times 10 to the power of 5. Okay, times V, which is given, 300 times 10 to the power of minus 6, divided by R, which is given, 8.31 times temperature in kelvins, 300. Okay, so this is number of moles at the beginning. So number of molecules at the beginning is equal Avogadro constant times number of moles, when Avogadro constant is given in your data booklet, is equal to 602 times 10 to the power of 23 times, of course, n, which was calculated here. So you know number of molecules. Is it clear? And we know that in each second, in 1 second, amount of molecules which escapes is 3 times 10 to the power of 19. And we have to find time after which half of the molecule will escape, because when half of the molecule will escape, then pressure will be reduced by half. So here we have to put half of n, half of this number. So by using simple proportion, this times this is equal to this times this, you can find time. So finally it will be half of number of molecules which is at the beginning divided by rate, which is 3 times 10 to the power of 19, and in this case time will be in seconds because all refers to the second. Clear? Okay, and exercise number 22, you had to try to do this. I hope that part of you tried. Okay, so let's do the last one, exercise number 22. So this one. Okay, we have a graph, and the point on the diagram represents the state of fixed quantity of ideal gas in a container with a movable piston. The temperature of the gas in the state shown is representing the new state of the gas after the following separate changes. A, by using blue. The volume doubles at constant pressure. Remember, PV equals nRT. So in this case we have pressure constant, number of molecules which is constant, and of course R is a constant, so must be constant. So if PV equals nRT and we have constant temperature, constant temperature, I wrote pressure. In first is constant temperature. Okay, so at constant temperature we have P times V is equal to constant because right hand of this equation is constant. So what does it mean? It means that P is inversely proportional to V. So if volume is 2 times bigger, then pressure is 2 times smaller. So new state will be somewhere here. So this is my A, capital letter of A. Okay, volume 2 times bigger, pressure 2 times smaller. And B, I'm going to use orange. Okay, the volume doubles at constant pressure. So now we have very similar, but pressure is constant. If pressure is constant, and of course the right hand of the equation is constant, okay, pressure is constant, N is constant, R is constant. So if volume changes, then something happens with temperature, okay? So we have to write volume is proportional to temperature because this is constant, this is constant, this is constant. So volume is proportional to temperature. Nothing happens with temperature. So in this case, on this graph, if volume is 2 times bigger and temperature... What? Yeah, Jesus, sorry, I did this completely wrong. I've read A. No, constant pressure, sorry, again, B, this is B, sorry. B, volume doubles at constant pressure. So it's easy, you don't need to do this reasoning. We have the same pressure, but volume which is 2 times bigger. So point B will be here. There is no temperature on this graph. So temperature is not important in this case. Of course, temperature is proportional to volume, but we cannot mark temperature on this graph. Okay, and C, I'm going to use red. Pressure halves at constant volume. Okay, so the same volume and pressure which is 2 times smaller, so point C is somewhere here. Again, we are not interested what happens with temperature because we cannot mark temperature on this particular graph. Yeah, I hope that it's clear. Let's do one more exercise which is quite difficult. Open your Tsokos, and of course I hope that you are prepared to the lesson. You have pen, pencil, calculator, ruler, and your notebooks and Tsokos. Yes? So now open your Tsokos on page number 141 and exercise number 23. So 23, 141. Okay. As I said at the beginning, we have a few solutions of this problem. I'm going to present you the most general one. Yes, we have 2 containers, and 2 ideal gases are kept at the same temperature. This is very important. The same temperature. Okay, in 2 containers separated by a valve, as shown in the diagram. Estimate the pressure when the valve is opened. The temperature stays the same. This is very important information. Okay, so let's name this container number 1, and this one number 2. Okay, remember base for ideal gas is Clapeyron's equation, which can be written in the form of, in the case of first container, as P1 V1 is equal N1 R times T. I don't need to put index in R because it is a constant, and for T because it is constant in this particular exercise. And P2 V2 is equal N2 R times T. Okay? What happens if this valve is open? Gas is mixed. Okay? So now we can write the same Clapeyron equation for situation when we have one container which contains an amount of molecules of this one, and which has a volume of these two containers. So generally we can write that when valve is open, then P multiplied by total V, which is V1 plus V2, is equal to total number of molecules N1 plus N2, R times T. Temperature is constant, so T has the same index. Is it clear? Okay. So we can write these two equations by using these units, 6 decimeters cubed and atmospheres. Okay, so let's write. In the case of first, we can write something like this. Pressure, which is 12 atmospheres, but we are not interested in the unit. Volume, which is 6, is equal to N1 R times T. In the case of second, we have pressure, which is 6, times volume, which is 3, is equal to N2 R times T. Okay? So let's back to this huge equation. Let's write left hand as pressure, we don't know, times volume. Volume is the sum of 6 and 3, so it is 9 in decimeters cubed. Is equal to, I'm going to eliminate bracket, the right hand of this equation, so N1 RT plus N2 RT. But N1 RT is 12 times 6, and N2 RT is 6 times 3. Okay, so finally we have 9P is equal to 12 times 6 is 72, plus 6 times 3 is 18, so 9P is equal to 90, so new pressure is 10, and the unit the same as here, so 10 atmospheres. Okay, remember this method, it's very important exercise. You have to write Clapeyron equation for one container, Clapeyron's equation for second container, and Clapeyron's equation for third container. Remember that total volume is the sum of volumes, and number of moles is also sum of number of moles. Yeah, I hope you tried to do this working alone. I didn't tell you, but it's obvious. If there is a kind of example from your book, please stop video, think for a moment. Try to do this alone. If it's not working, then turn the video back and check my method. Okay? So now, please copy this to your notebook. You have, let's say, 4 minutes. Analyze this exercise one more time. Copy this, read it again, try to solve it working alone. Remember, it's very, very important exercise. So to highlight this very, very important exercise, I'm going to make a three-dimensional sign of importance. Okay, and you will be ready. Turn video again, and let's focus on last problem. Okay. I need this slide. And this slide. Okay. Okay, you can write the last point or last lesson, Boltzmann equation. Okay, ready? So first of all, we have new constant today, constant called Boltzmann constant, small k with index of b. Boltzmann constant is the product of two other constants, gas constant, which you know, and Avogadro constant, which you know. So when you divide gas constant, which is given in your data booklet, by Avogadro constant, then you will obtain Boltzmann constant, and Boltzmann constant is also given in your data booklet. It's here. Okay, and what is a Boltzmann equation? Boltzmann equation links average kinetic energy of the molecule of a gas, yes, with temperature, absolute temperature in kelvins. You know from middle school then when there is a higher temperature, then molecules of the gas move faster. When there is a lower temperature, then molecules of the gas move slower. Okay, so there must be a kind of link connecting kinetic energy or speed of the molecules, average, with temperature in kelvins. So what is how to derive it? The method you have in your Tsakos on page number 138. But let's analyze this method with me. Okay. So what is this? I'm going to use Ke with dash, okay, as average random kinetic energy of the molecules. Okay, average random kinetic energy of molecules. Okay, so what is this average random kinetic energy of molecules? If you have, let's say, n molecules, you have to add kinetic energies of all n molecules and divide this by number of molecules. Is it clear? Okay, if each molecule travels with average speed of v, then you have half of mv squared plus half of mv squared plus half of mv squared divided by n. Okay, but let's look. In your Tsakos, you have something like distribution of speed. Okay, so what does it mean? It means that each molecule can travel with little bit different speed. We are talking about average speed, but it doesn't mean that all molecules travel with exactly the same speeds. Okay, if speed of the molecule is bigger, then this particular molecule, the temperature of this particular molecule is a little bit higher, or corresponding temperature is higher. But in average, yes, and in average, temperature is proportional not to squared speed, average squared speed. Is proportional to the average kinetic energy, because speeds can be different. So let's look. So let's take it and write in the form of half of m divided by capital N, and in the bracket we have v1 squared, v2 squared, v3 squared, etc., etc., up to vn squared. Is that clear? Okay, so here we have something like not average squared speed, but something which is called a root mean square speed. Okay, so it's not exactly the same. So let's focus on this, and maybe let's write this n here. It will be a little bit easier. Okay, so what is this this part? This part, yeah, is known as average root mean squared speed. Root mean square speed. Okay, which is not exactly the same as average speed, because in the case of average speed you have to add all speeds, okay, and divide this by number of molecules, so by n. In this case you have to add all squared speeds and divide this by n. Is it clear? So this is square root means square speed. Okay, so remember about this, that this c is not average speed, but something calculated by using this method. This is the sum of squared speeds divided by n. Okay, please copy this to your notebook when you will be ready. Turn the video again, and I'm going to talk about this. Okay, I hope you're ready. Okay, so let's look. Let's take this, remove, and start with this. Okay, let's start with Clapeyron's equation. Of course, you know that P, pressure, times V, volume, is equal N R T. N is number of moles, R is gas constant, and T is a temperature. Is that clear? Okay, and there is one more equation. You don't, in one hand, you don't need to memorize it, but in other hand, you must know how to derive this. So practically, you must know this. Pressure of the gas can be also written in the form of one-third times density times this squared speed. Okay, and so let's substitute here, and we have 1/3 rho c squared v is equal nRT. Okay, we know that density is mass over volume. Okay, so it can be written as 1/3 mass of the gas over volume of the gas times c squared times v is equal nRT. Okay, there is another mistake in the Tsokos. You see, its denominator is written wrongly. Okay, v in denominator and c squared and v is here. Okay, next line. We can cancel the volume. Yes, obtaining 1/3 mass c squared is equal to nRT. Okay, now we can substitute that mass is number of molecules times mass of one molecule. Yes, this is first. And second, that the number of moles is number of molecules divided by Avogadro constant. This is second, you have to notice. Okay, substitute, we have 1/3, except m, we have number of molecules times mass of molecule times squared speed is equal to, except number of moles, we have number of molecules divided by Avogadro constant times R times T. We can cancel n. Okay, and the last one, we can use this Stefan Boltzmann constant. Substitute that Boltzmann constant is R over NA, obtaining at the end, at the almost end, 1/3 mc squared is equal R over NA is K, so K with index of B times T. Okay, and multiply all by 3/2, obtaining 1/2 mc squared is equal 3/2 constant times temperature, or finally that average kinetic energy of the molecules is equal 3/2 Boltzmann constant times temperature. And this equation, which links average kinetic energy of molecules with temperature, is known as a Boltzmann equation. Okay, and due to this, definition of temperature. Temperature is the measure of the average kinetic energy of molecules in the substance. Okay. Okay, what is the consequence of this equation? And consequence of this equation is fact that there must be the lowest possible temperature equals 0, where average kinetic energy of the molecules is equal to 0, which means that molecules do not move. Please copy this to your notebook. When you will be ready, we will do one example, okay? Few minutes later, I hope that you finished. So let's find a kind of example related with this. Here. Okay. Let's take 32 average speed. Oh, helium atoms. The molar mass of helium is 4 grams per mole. Okay, these are one of this. Let's say exercise number 32A, because exercise number 30 will be your homework. Okay, so 32A. Calculate the average random kinetic energy of a gas kept at temperature of 300 kelvins. Okay, so average random kinetic energy in one side is given by half of mv squared, in other is 3/2 Boltzmann constant times temperature. So we can, if we have temperature, we can calculate this by using 3/2 times Boltzmann constant, which is 138 times 10 to the power of minus 23. Unit is joule per Kelvin, times 300 kelvins. Remember, in this equation, temperature is in kelvins, so by multiplying this 3, this, and this, you have final answer. Clear? Okay, so now maybe let's do together exercise number 30. Okay, so Tsokos, page number 141, exercise number 30. Your task is to find the average speed of helium atoms at temperature 850 kelvins. The molar mass of helium is 4 grams per mole. Okay, you have, let's say, 6-7 minutes to solve this problem. Yes. Turn off video for 7 minutes, copy this to your notebook, try to do this. When you will be ready, turn video again, and I give you a solution and you will check. Okay, so 7 minutes later. You have to find first average kinetic energy by using the same equations we did in exercise number 32. So 3/2 times Boltzmann constant times temperature in kelvins is, of course, average kinetic energy of molecule. Temperature is given in kelvin, so you don't need to convert it. Okay? So if kinetic energy is given, you can use another equation, that half of mass of molecule times average squared speed, this Rodman squared, is equal to average kinetic energy. Then to find V, you have to know two. You have to know m, mass of the molecule, and you have to know kinetic energy average, which is given. So all you have to do here at this moment is find mass of one molecule of helium-4. We have one more parameter, yes, that 1 mole has a mass of 4 grams. And you know that 1 mole contains Avogadro constant of molecules, and Avogadro constant is 602 times 10 to the power of 23. Or basically, 4 grams of helium-4 contains 6.02 times 10 to the power of 23, and remember that 4 grams is 4 times 10 to the power of minus 3 of kilograms. So I can build a simple proportion. that 6.02 times 10 to the power of 23 molecules has a mass of 4 times 10 to the power of minus 3 kilograms. So one molecule has a mass of x. Use simple proportion to find x. X will be a mass of one molecule. Okay, so it will be this 4 times 10 to the power of minus 3 divided by this 6.02 times 10 to the power of 23, and the result will be in kilograms. So finally you can calculate speed, okay, as 2 times kinetic energy average divided by m and the square root of where kinetic energy was calculated here and mass of one molecule was calculated here. Okay? And speed will be given in meters per second because we've used standard units. Mass in kilograms and kinetic energy here in joules. Yeah? Okay, I hope you did this exercise correctly. If not, please copy this to your notebooks or correct your writing. And as you see, we've finished the chapter. Okay? So now your homework is to do first 10 exercises, A, B, C, D, so multiple choice exercises. It's SOCOS page number 142 and 143. Okay, so homework. SOCOS 142, 143, exercises from 1 to 10, all multiple choice. Okay, you have one day because next lesson is at Thursday. So it's not time consuming. You have to spend with this not more than 20 minutes. So upload your answers only A, B, C, D, or you can write, you don't need to upload as assignment. Please write in the comment like 10 letters, like A, B, C, D, A, B, C, D, something like that. Okay, it's obligatory. So next lesson at Thursday we will focus on the exam style questions, and it will be finish of the chapter. I have to think about kind of test how to solve the problem of your grades. As you see, the chapter is not too long, in my opinion, the shortest and the easiest. Okay, so good luck with your homework. I hope that you like this video. Please write any suggestions and comments on the YouTube channel or directly in the classroom, Google Classroom. And remember, learn physics and stay at home. Bye.